So this is gas volumes, which is on pages in your textbook, on pages 14 and 15. Pages 14 to 15 in your textbook, okay? But before we do this, I just want to have a quick recap on moles so far. So what we know about moles so far. So we know that the relative molecular mass in grams equals 1 mole. Okay, we also know that the equation, when you're doing calculations with moles, that the equation that we use is moles equals mass over molar mass. Okay, so we've done this previously. Okay, we also know that the molar mass is the grams per mole. Molar mass is grams per mole for every mole. Okay, and so this is effectively, it's the same thing as the relative molecular mass in grams. So if I was to say to you, what's the relative molecular mass of water, you would say 18 is the relative molecular mass of water, because you would just add up the relative atomic masses. You just go 16 for oxygen, and there's 2 hydrogens, 2 times 1, and that is 18. Okay, if I said to you, what is the molar mass of water, the mass of 1 mole, what's the molar mass of water, it's exactly the same number, but it's grams for every mole. Okay, another thing we've done, just to revise before we move on, is Avogadro's constant. Avogadro's constant, okay, which says that 1 mole of anything has got, if it's, for example, if you have, say, 1 mole of carbon atoms, is the relative atomic mass in grams is 12 grams, and that is 6.02 times 10 to the 23 carbon atoms. Okay, 1 mole of water molecules, for example, 1 mole of water molecules is 18 grams, is 6.02 times 10 to the 23 water molecules. And that's Avogadro's constant. Okay, so that's what we've done with moles so far, all the work we've done. And when you're doing this equation here, it's really helpful if it's a solid, because if it's a solid, it's very easy to weigh and get the mass of a solid. But if we're going to be talking about gases now, it's very difficult to weigh gases, and instead of weighing them, it's easier to get the volume of a gas. So we need a different relationship in order to work out the volume of a gas rather than weigh it. Okay, which is what this little video is about. So for gases, we do a different equation, and this has all come from Avogadro again. Okay, Avogadro also worked with moles and gases, and Avogadro said that the volume of a gas at room temperature and pressure contains equal numbers of molecules. Okay, so he said it doesn't matter which gas is being measured. Okay, if you have 24 decimeters cubed of a gas, then that is 1 mole of gas. So if you've got 24 decimeter cubed of gas, that is 1 mole of gas. And it doesn't matter which gas it is. So if it is like hydrogen gas, or if it is oxygen gas, if it is carbon dioxide gas, okay, 1 mole occupies 24 decimeter cubed, that they're all 1 mole, occupies 24 decimeter cubed. And that's the relationship that Avogadro came up with at room temperature and pressure. So just going to make a little note here. Okay, so at room temperature and pressure, so I'm going to put RTP, which means at room temperature and pressure. Okay, room temperature and pressure, 1 mole of a gas occupies approximately, because it's not exactly, but it's approximately 24 decimeters cubed. And this is a way we work out moles, but for gases, okay, because it's easier to do a volume. This is a volume, okay, but exactly the same as previously. 1 mole is the relative molecular mass in grams. So if 1 mole's relative molecular mass in grams, this is going to be 2 grams. 2 grams of hydrogen is 1 mole and will occupy the volume 24 decimeter cubed. O is 16, so that'd be 32 grams. 32 grams of oxygen is 1 mole and occupies a volume of 24 decimeter cubed. Carbon dioxide is 44 when you add it up, 12, 16, 16. 44 grams of carbon dioxide is 1 mole, occupies a volume of 24 decimeter cubed. Okay, so you can see that for the same volume, that the hydrogen gas is a much lighter gas than oxygen and carbon dioxide for the same volume. Okay, now this volume is in decimeter cubed, right? But what does that actually mean? What does a decimeter cubed mean? So 1 decimeter cubed, what does it look like? What does it actually mean? So 1 decimeter cubed is the same as 1,000 centimeters cubed. Okay, 1,000 centimeters cubed, which in the old units we used to use was a liter. That was a liter in the old units. But what does 1,000 centimeters cubed look like? Now remember the work we've just been doing with a hydrated salt, and you used a volumetric flask to make a standard solution. You used a volumetric flask to make a standard solution, and that volumetric flask had a volume of 250 centimeters cubed. So when you're thinking about what does 1,000 centimeters cubed look like, it's like 4 volumetric flasks, and that is a decimeter cubed. And if you imagine now a volume of, if you take that decimeter cubed and times it by 24, you've now got 24 decimeter cubed. So it's Avogadro who came up with this relationship again, that the 1 mole of any gas occupies 24 decimeter cubed. But this is at room temperature and pressure. Okay, room temperature and pressure. So how do we actually do calculations with this? So in order to do calculations when we've got a gas, we need to use a second equation, right? Remember, we've got the first equation, moles equals mass over molar mass, which is really good when you've got a solid, or obviously when you've got a mass of something. But we need an equation for volumes when we're measuring a gas volume. Okay, because we could measure it using a syringe or a measuring cylinder. So the equation we use is moles of a gas, so this is just for gases, it's only for gases, moles of a gas is the volume of the gas divided by 24 decimeter cubed. Okay, but if that's really large, big scale if you'd use 24 decimeter cubed, so maybe we might want to use this one instead. Moles of a gas is the volume of a gas, not a liquid, it's volume of a gas, over 24,000 centimeters cubed. Okay, so if the gas that you're measuring is in decimeter cubed, you use that equation. If the gas you're measuring is in centimeters cubed, then you use that equation. Okay, so we're just going to have a practice question. and have a go at that. Okay, so I've got a practice question here. So, what is the volume? So the question is, what is the volume? What is the volume of 1.282 grams of sulfur dioxide gas at room temperature and pressure? Okay, so you've got two choices now. You can press the pause button and have a go at this yourself using those two equations. Moles equals mass over molar mass, and moles equals volume of a gas divided by 24 decimeter cubed. So you can pause it and then check your answer in a few moments, or you could just watch how I do this first question. Okay, but I think you should pause it. All right, so we've got a mass of a gas, So we say moles equals mass of the gas over molar mass. Okay, so we've got the mass of the gas, 1.282, over the molar mass of sulfur dioxide. So you need to work that out. It's sulfur is 32.1, oxygen is 16, and there's two of them. And so together that totals 64.1. Okay, so you work that out, 64.1, and it comes to 0.02 moles exactly. Okay, 0.02 moles exactly. Remember what we're trying to find? We're trying to find the volume of the gas. So then we take the moles, and we use this equation now. Moles equals volume of a gas, and we divide it, let's do 24 decimeter cubed, doesn't matter which units you use. So that's the equation we're going to use. So we've got the moles, so we're going to go 0.02 moles equals the volume of the gas, which is what we're trying to find, divided by 24. So it's dividing on this side, so you bring it up and times it, you do the opposite on the other side, bring it up and times it, so it's going to be 0.02 times 24 equals volume, and that answer is going to be, when you multiply those, the volume equals 0.48 decimeter cubed. It is so important that you put the units, because it could be centimeters cubed or it could be decimeter cubed. So what we've done in this calculation is we've gone from a mass of a gas through using two moles equations. We're using two moles equations, we've turned it into a volume. So when you're doing calculations, you can turn a mass of a gas into a volume, because it's much easier in experiments to use a volume of a gas rather than to weigh a gas. Okay, one more example, last one. Last example. So, and this time you've definitely got to press the pause button and have a go at it. Okay, question, what is the mass of 1,920 centimeters cubed of this gas here, C3H8. Okay, and this is a gas, and it's at room temperature and pressure again, so we're using the same equation. Okay, C3H8. What is the mass of that volume of C3H8? Okay, which is that's propane, which you might recognize that, propane. All right, so using the two equations, press the pause button and have a go at the calculation. We've got a volume, so I'm going to use the equation moles equals volume of a gas over, it's in centimeters cubed, so I've got to use 24,000 because it's in centimeters cubed. Okay, remember 1 decimeter cubed is 1,000 centimeters cubed. Okay, so we do that calculation, comes out at 0.08 moles. Okay, and then let's get that calculation. Then you go, okay, 0.08 moles equals, because we're trying to find the mass, equals mass over molar mass. And you've got to work out the molar mass of propane. So carbon is 12, 12 times 3, hydrogen is 1, so 1 times 8. You add that up and it comes to 44. So you go, okay, mass over 44, and it's divide, so take it over to the other side and times it. 0.08 times 44 equals mass. Okay, so that answer is going to be, the mass is going to be, mass equals 3.52, and you have to put units. You have to put units, otherwise it's not going to make sense. Is it grams? Is it kilograms? What is it? Okay. Now the reason why we do these moles calculations is so that when we do an experiment, we know how much material to start off with, we know how much product we're going to make, how much reactants we need at the start, how much product we need at the end.